Hi students, Miss Vernon, and today I'm here to teach the final lesson in this set of learning, which is 2.5, Day 2. Today we're going to continue to talk about complex zeros. We're going to talk about how to do synthetic division with complex zeros, and just kind of put the whole process back together. So I have two big examples for you today, and we'll go ahead and get started. As you're working through these examples with me, I really want to stress that you'll want to make sure you have a good amount of paper because they will take a bit of work. And again, I'm just going to kind of summarize the full process. So in this example, it says find all the zeros. So we know we want to find out all the x-intercepts of this polynomial, which is written in standard form. And then we want to write f of x as a linear factorization. So that means I want each parenthesis term to be x plus something or x minus something. So we're going to go ahead and start this process by determining the potential rational roots or rational zeros. And so I call those my PRs. This is the one where we take P divided by Q. So in this case, P is going to be 8 and Q is going to be this invisible 1 that is sitting in front of the X term. So when I list my factors of 8, I know 1 times 8 and 2 times 4. So those are all the factors of 8. And then Q was 1, so 1 times 1 is the only factor. So my possible rational zeros are going to be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Once you've identified your possible rational zeros, the next thing I tell students to do is to graph it. Now you can see I've already included the graph here. And as I look at this graph, I can clearly see the graph is crossing in 3 spots. Now, I'm a little perplexed by this because if it crosses in 3 spots, I am perplexed because this is a degree 5 polynomial. And because it's a degree 5 polynomial, I know I should have up to 5 zeros. But because I'm only seeing 3 of them, it's kind of indicating that 2 of them are going to be complex, which would make sense because we know complex zeros come in pairs. So now I need to start to break down this 5th degree polynomial into linear factors. So as I look at my graph, I see that that appears to be crossing at -2, which is one of my possible zeros. This looks like it's crossing at 1, and then I have 2, 3, 4. So that appears to be crossing at 4. None of these look like they are hugging or kissing of the graph, so I'm going to go with these are all zeros that show up once and are not multiplicities. So now that I've identified what my possible zeros are, I'm going to go ahead and set up my top line of my synthetic division and test them out. So remember, with synthetic division, we take the coefficients from in front of each of our terms, and I put them in the top line of my synthetic division. There's a lot, and I want to make sure I don't mess up my signs. And then I have now set up my base synthetic division. So at this point, what I'm going to do is I'm going to start by testing the different zeros that we've identified. I'm just going to start with the leftmost one, which was -2, and I'm going to apply my synthetic division. So I drop down the 1, and then I multiply, and then I add. Remember, with synthetic division, we do always add. All right, then I multiply the number I just got by the number on the shelf, and again, I add, and I continue to do this process. Multiplying and adding. And my goal is that when I do the final phase of this, that I get a 0. Remember that this means there's a remainder of 0. So therefore, I can state that this was a 0. And if that's a 0, I then know that x plus 2 is a factor. So I'm going to just kind of identify that this is going to be a factor of our polynomial. Now, what we're going to do next is a little different than what we've done before. When we want to factor a 5th degree or a 4th degree, we want to take our previous line of answers or our previous answer line, and we're going to apply our synthetic division to that. And what it's going to allow us to do is it's going to break down our polynomial and allow for us to figure out what is left. So normally we would say this is your constant, this is your x term, x squared, x to the 3rd, x to the 4th. But we want to factor out another x. So I'm going to apply the synthetic division with the next 0 listed that we suspect from our graph, which is 1. Again, I'm going to drop down that purple 1. I'm going to multiply, and then I'm going to add. Remember, synthetic division we add. I'm going to do -5 plus 1 is -4. Multiplying and adding gives me a 1. Multiplying and adding gives me a -4. And multiplying and adding gives me a 0. This is, again, a very good sign because what this means is that 1 was also going to be a 0. And if 1 is a 0, that means x minus 1 is a factor. So you can see I'm kind of listing my factors as we continue working with this polynomial. So just like we've done so far, I'm going to take that last line, that last orange answer, which would be constant x, x squared, x to the 3rd. This would be our x to the 4th, and then this factor would be our x to the 5th. But I'm going to go ahead and do synthetic division with the 4, because again, the graph appears to be crossing at 4. And I'm going to apply that to the orange, or the very last line that I just got. So I drop my 1, I multiply, and then again, remember, synthetic division, we're adding. So I get 0 out. 0 times 4 is 0. 0 plus 1 is 1. 1 times 4 is 4. 4 and -4 is 0. I am doing my happy dance over here because what this tells me is that 4 checked out. It is indeed a 0. And by doing my synthetic division in this way, it allowed for me to identify a 3rd factor that is a rational 0. So at this point, I can combine all of this information and I could write my function, and my function would be x plus 2 times x minus 1 times x minus 4. And then I can take this previous line. This is my constant, this is my x term, and this is my x squared term. And I would have x squared plus 1. Now, this is almost considered to be linear factors. The first 3 are linear, but this 3rd factor is what we call a quadratic factor because it's being squared. Our directions for this problem did say to write it as a linear factorization and to find all of our zeros. So to continue moving us in the direction of finding our zeros, what I'm going to do is I'm going to take this squared factor and I'm going to set it equal to 0. Now, normally, if I had a middle term or a middle x value, I would want to use the quadratic formula to solve this because we already know there aren't any more rational zeros and I'm not seeing any more real zeros on the graph, so therefore it's probably going to be a complex 0. And those are only found with the quadratic formula. However, this one does not have a x term, so I can just solve this like I normally would by balancing. So I have x squared equals -1, and then taking the square root of both sides, I get x equals plus or minus I. So remember, when I take the square root of -1, I get I out. So I can take that information, no pun intended, and I can write this in fully linear factorized form or as a product of linear factors, and it would look like this. X plus 2 times x minus 1 times x minus 4. Those were the 3 zeros we did synthetic division to find. And then I just algebraically solved and found that I had x minus I and x plus I as my remaining 2 linear factors. So this is my linear factorization, and my zeros are x equals I, x equals negative I, x equals negative 2, x equals 1, and x equals 4. All right, so that is the first of our two examples. Again, I know this was a lot of work, a lot happening, so I'm just going to really encourage you, if you need to, press pause and take down notes. And then if you have questions, be sure to let me know what those questions are. All right, our second example of today is going to be, again, another problem that really requires us to use our brains. It's going to be a lot of work, and it's going to take up a fair amount of paper. When I worked this one out, it took almost an entire piece of notebook paper. So I'm really going to encourage you, make sure you set yourself up for success by having enough space to write. So in the second example, I am telling you that we have a complex number or a complex zero, x equals 1 minus 2i, and that this is a zero of this polynomial. Now this is a degree 4 polynomial, so therefore I know I am looking for 4 zeros. Now those zeros might be real, they might be irrational, or they might be complex. We know for sure one of the zeros is complex. We want to find the remaining zeros of f of x and then write it as a linear factorization. This linear factorization is going to get a little messy, so just stay tuned with me. Now, one of the first things I noticed about this polynomial is that it has a fourth degree but no third degree. So right off the bat, I want to make sure that I note that 4x to the fourth plus 0x to the third plus 17x squared plus 14x plus 65. If you forget to put in this 0, it's going to make it harder for you to solve this problem because you haven't marked the x to the third position in the exponents. Now, typically, we would start by listing our possible rational roots. However, because they're giving us a 0, we're going to start by doing synthetic division with what we know. And we know that one of our zeros is x. One of our zeros is going to be x equals 1 minus 2i. But because we know that zero, we also know a second zero. We also know that its conjugate is also going to be a 0. So we can also divide it by 1 plus 2i. Because I know two of the zeros, I'll be able to factor this to a quadratic where I'll be able to use the quadratic formula. So let's go ahead and get started. We're going to do synthetic division with the first zero they gave us, which was 1 minus 2i. I'm going to go ahead and list my coefficients. So I have 4, 0, 17, 14, and 65. Again, I'm just going to double check that I didn't make a mistake with any of my signs. So I'm just going to look up at the original problem, make sure I have all the right signs. Yep. And then notice I've left a lot of space here. I did that for a reason. And then I'm also going to just make a note that over here, this is going to be where we kind of do some scratch work. So we're going to do some math on the side because this is going to get a little messy. All right, so starting with our synthetic division, I'm going to drop the 4 down, and then I'm going to multiply 4 times 1 minus 2i. That means I'm going to have 4 times 1, which is 4, and 4 times negative 2i, which is negative 8i. We learned that when we are combining complex numbers, we add the real parts and we add the imaginary parts. In this case, it just becomes 4 minus 8i. Next, I'm going to take that times what's on the shelf. This is where that scratch work is going to come into place. So I'm going to take 4 minus 8i times 1 minus 2i. And when I do this multiplication, I'm going to have 4 times 1, which is 4. 4 times negative 2i, which is negative 8i. Negative 8i times 1, which is negative 8i. And negative 8i times negative 2i, which is positive 16i squared. Now recall, an I squared makes that term negative, so really this is like saying minus 16. Combining my like terms, I have 4 minus 16, which is negative 12, and negative 8i and negative 8i, which is negative 16i. I'm going to go ahead and put that under the 17, so I have negative 12 minus 16i. I'm going to combine the real parts, so that gives me 5, there is no imaginary, minus 16i. Now you might say, Miss Vernon, this is going to take forever. The first time around, it does take a little bit, but you're going to see that it gets much easier very quickly. So again, we're going to take that answer times the number on the shelf. So we have 5 minus 16i times 1 minus 2i. And we're going to do our multiplying. So 5 times 1 is 5. 5 times negative 2i, which is negative 10i. Negative 16i times 1, which is negative 16i. And negative 16 times negative 2 is positive 32. And then we had an I on each of them, so I squared. Again, I squared is like a negative 1, so this really becomes minus 32. So we now have 5 and negative 32, which is negative 27, and negative 10 and negative 16, which is negative 26i. So I'm going to put that under the 14. So negative 27 minus 26i. I'm going to add these up. And when I do this, I got negative 13 minus 26i. Now, you might be saying, Miss Vernon, there is no way this is going to work out nicely. It hasn't worked out nicely yet. Well, hold steady. Let's see what happens. So we've got negative 13 minus 26i times 1 minus 2i. And we need to do our multiplication here. So negative 13 times 1 is negative 13. Negative 13 times negative 2i is positive 26i. Negative 26i times 1 is negative 26i. And negative 26i times negative 2i is a positive 52i squared. And again, because we have an I squared, we know this really is minus 52. And notice that our positive and negative i's, 26i and negative 26i, add to 0, so I end up with negative 65. Well, now, friends, I want to remind you, I told you from the start, this was going to produce a 0. So I'm really glad it worked out. Now what we're going to do, yep, you guessed it, we need to do synthetic division with 1 plus 2i, its conjugate. Now, I know some of you are probably sitting there going, no, don't make us do that. But I promise you, you're going to see something really cool happen. So let's go ahead and follow the process. So drop down the 4 and then multiply by it. 4 times 1 is 4. 4 times 2i is positive 8i. If we combine the real parts and the imaginary parts, we get 8. So pretty. All right, let's do the math again. 8 times 1 is 8, and 8 times 2i is positive 16i. Adding the real parts and the imaginary parts, we get 13. This is so great. Let's keep going. 13 times 1 is 13, and 13 times 2i is positive 26i. Hey, that adds to 0. Look at that. It did work out. And the second round of it was much easier. So now that we are to the point where we've successfully identified 2 of our zeros, what's happened is we've now broken this down to a point where we have a quadratic left. This is 4x squared plus 8x plus 13. And whenever we have a quadratic equation, the fastest way to solve it is either by factoring, and if that doesn't work, then using the quadratic formula. If I tried to solve this to find my remaining zeros by factoring, I would need to find 2 terms that add to equal 8 and multiply to equal 52. I checked, none of them work. This is not factorable, or this is a prime polynomial. So to finish solving this, we are going to have to rely on the quadratic formula. So what we're going to do is we have our A, our B, and our C value, and we're going to plug it in. So x equals negative b plus or minus the square root of b squared, notice I put that in parentheses just in case it was negative, times 4 times a times c, all divided by 2 times a, or 2 times 4. All right, let's continue to simplify this. I like to put everything under the square root into the calculator. And when I did that, I got negative 144. Continuing with our simplifying, I have negative 8 plus or minus. The square root of 144 is 12, and because it was negative, we have to attach an I to it. Divided by 8. Last but not least, we need to simplify this by dividing each term on top by what is on bottom. So negative 8 divided by 8 is going to give us 1. And 12i divided by 8 is going to give us 3/2 I. I divided the 12 and the 8 by 4 to get 3/2. There are my remaining 2 zeros. All of these zeros are going to be complex. Ay, ay, ay. So let's take a second and write this in linear factorized form. We have x minus 1 minus 2i. That was the first one we divided by. Then we have x minus 1 plus 2i. That was the second one. Then we have x minus 1 plus 3/2 I. And then we have x minus 1 minus 3/2 I. Wowzers, that was a tough problem, but we did it and we trusted the process. Dividing by a complex number isn't always easy, but it does work out if you combine your skills of multiplying complex numbers, adding like complex numbers, and trusting the process of synthetic division. I hope this is making sense, and you have a great day. Bye now.